Jemason tutorials. In this session we focus on sequences and series, and this particularly has to do with recurring series. The question says a sequence un such that n is an element of natural numbers is given by u not equals -1, u1 equals half, un plus 2 equals un plus 1 minus 1/4 un. Let two other sequences be Vn and Wn defined by Vn equals un plus 1 minus half un and Wn equals un all over Vn. Calculate V0 and W0. B. Show that the sequence Vn is a geometric progression and state its common ratio. C. Express Vn in terms of n and hence evaluate the limit as n tends to infinity of Vn. D. Show that Wn plus 1 equals Wn plus 2 and characterize the sequence Wn. E. Express Wn in terms of n. F. Show that for all n elements of natural numbers, un equals 2n minus 1 all over 2 to the n.
Okay, in the first part, the A part says we should calculate V0 and W0. For V0, we go to the expression that has Vn and replace every n by 0. So V0 should be u0 plus 1, which is simply u1 minus half u0, and u1 is given as half in the equation minus half into u0, which is -1. All that gives half plus half, which is 1. Therefore V0 equals 1. For W0, we go to the expression that has Wn and replace every n by 0. We have u0 over V0. u0 is -1 and V0 we are just from getting as 1. And that gives -1. So W0 equals -1. In the B part, we are asked to prove that Vn, we are asked to prove that Vn is a geometric progression and then state the common ratio. For Vn to be a GP, geometric progression, Vn plus 1 all over Vn should be a constant. And that constant is supposed to be the common ratio R. So we get the expression for Vn plus 1 and divide it by Vn. Now at the numerator, Vn plus 1 is obtained by going to the expression for Vn. Again, I'm replacing every n by n plus 1. So Vn plus 1 should be un plus 1 plus 1, which gives un plus 2 minus half un plus 1 all over Vn, which is given in the equation as un plus 1 minus half un. Now we need to make a replacement for the higher term, which is un plus 2, and it's given in the equation that un plus 2 equals un plus 1 minus 1/4 un. So we replace it un plus 1 minus 1/4 un. That is the replacement for un plus 2. Then minus this other term, half un plus 1 all over un plus 1 minus half un. This gives un plus 1 minus half un. A whole minus half gives half, so half un plus 1 minus 1/4 un all over un plus 1 minus half un. In the next step, This ratio, once we are seeking to show that a sequence is a GP, arriving a situation like this, we just have to factorize and then a common factor will cancel. You can see that the denominator is already simple. We can factorize the numerator. Obviously, the coefficient of un plus 1 being unity at the bottom, we also seek to make it unity at the numerator, and that will be done by factorizing half. So half into, at the numerator I divide every term by half, I get un plus 1 minus 1/4 divided by half gives half of un. All that divided by un plus 1 minus half un. You can notice that the numerator, the factor there cancels the denominator. Now we have that vn plus 1 all over vn equals half, which is a constant. So in conclusion, we say since vn plus 1 all over vn equals half, a constant, vn is a GP with common ratio being half. As the question said, we should state the common ratio. In the C part, we are then asked to express Vn in terms of n and hence evaluate the limit. So Vn in terms of n, once a sequence is being asked, once you are asked to express a sequence in terms of n, it usually most of the time is in the case where you have established that it is either a GP or an AP. And this then is simply asking for you to find the general term or the nth term. So Vn being a GP, then the general term Vn should be equal to, normally the general format is the first term into the common ratio raised to the power n minus 1, where n is the number of terms. But we know that the first term of Vn is V0, and V0 is 1. Once a sequence starts with V0, for example, the term when n equals 0, then there should be n plus 1 terms. So the number of terms is actually n plus 1. And so we are going to have that Vn equals the first term, as the general formula says, the first term, which is V0, into the common ratio raised to the power capital N minus 1, and n in this case is n plus 1, because there are n plus 1 terms. It has to be the number of terms minus 1. So n plus 1, then minus 1. So that gives us V0 r to the n, simply. Therefore Vn should then be V0, which is 1, into r, which is half to the power n. And that simply gives us 1 all over 2 to the n as Vn in terms of n. We are then asked to find the limit as n tends to infinity of Vn, which is simply limit as n tends to infinity of 1 all over 2 to the n. And a direct substitution of infinity gives 1 all over 2 to the infinity. 2 to the infinity is a very large number given the notion of infinity. And so we have 1 all over infinity, which is 0. Therefore, limit as n tends to infinity of Vn, as the question has asked, equals 0. In the D part, we are asked to show that Wn plus 1 equals Wn plus 2. So begin with Wn plus 1. Remember, Wn is given as Un over Vn. So Wn plus 1 should then be Un plus 1 all over Vn plus 1. And that gives, now Un plus 1, according to the information we have, there are two expressions that have n plus 1. The first one, which has Un plus 2 equals Un plus 1 minus 1 quarter Un. And the second one, which has Vn equals Un plus 1 minus half Un. The first one having a very high term Un plus 2. If we take that option and make Un plus 1 the subject, we might have difficulties. So we take a simpler one which has smaller terms. Un plus 1 can be made the subject in this other one containing Vn. And so Un plus 1 there should simply be Vn plus half Un. And Un plus 1 is made the subject. Divided by Vn plus 1, which is simply obtained by replacing every n by n plus 1 in the expression for Vn. So we get Un plus 1, which gives Un plus 2 minus half Un plus 1. This will give Vn plus half Un at the numerator all over Un plus 2. Again, it is given in the equation as Un plus 1 minus 1 quarter Un. So we replace it Un plus 1 minus 1 quarter Un, and then minus half Un plus 1. This gives Vn plus half Un all over Un plus 1 minus half Un gives half Un plus 1 minus 1 quarter Un. This gives Vn plus half Un at the numerator all over. Again, the numerator has simple terms, and at the denominator we have Un plus 1, which has a replacement again. We go to the expression for Vn and make Un plus 1 the subject. So we should have half of Un plus 1. So Un plus 1 was replaced down. Un plus 1 equals Vn plus half Un, as we had already in the D part. So we replace it with Vn plus half Un, then minus 1 quarter Un. And this gives Vn plus half Un all over half times Vn is half Vn. Half times half Un gives 1 quarter Un, and then minus 1 quarter Un. And this gives Vn plus half Un all over 1 quarter Un minus 1 quarter Un will disappear, and we just have half Un. We divide every term. Give half Vn, sorry. We are just left with half Vn as the denominator. Dividing every term by the denominator, we get Vn over half Vn. That gives 1 all over half plus Un over Vn. Therefore, Wn plus 1 equals 1 all over half is the same as 2 plus Un over Vn, which is supposed to be Wn. And that is what we are asked to prove in the D part. In the E part, we are asked to express Wn in terms of n. Remember, in the D part, the question required that we should characterize Wn after this expression proven. And from there, we can see that Wn plus 1 should be equal to Wn plus 2, which follows that Wn plus 1 minus Wn equals 2. And this is a constant, showing that Wn is an arithmetic progression. It's an arithmetic progression with common difference 2. And so now to express Wn in terms of n, it becomes easier since Wn has been established to be an arithmetic progression. Wn should then be generally the first term plus number of terms minus 1 times the common difference. That simply implies that we have W0 plus, since the first term is W0, the number of terms should be n plus 1 and then minus 1 times the common difference, which is 2. So we get W0 plus n plus 1 minus 1, which gives 2n. So W0 into the number of terms, which is n plus 1 minus 1 times the common difference. W0 equal, so that will give W0 plus 2n, which is this. Therefore, W0 equals 2n minus 1. So that is W0 in terms of n as the E part specifies. In part F, we are asked to prove that Un equals 2n minus 1 all over 2 to the n for all n elements of natural numbers. In order to prove the general term of a sequence, which is defined recursively, we have to make use of the recursive relationship. It is given as un plus 2 equals un plus 1 minus 1/4 un. That is the recursive relationship in which un has been defined. So we have to use proof by induction. I will start when n equals 0. We have that u0 equals 2 into 0 minus 1 all over 2 to the 0, which is 0 minus 1, negative 1 over 1, which is negative 1. And that is true because in the equation u0 is negative 1. Now we assume that uk plus 1 and uk are true, so that we then prove that uk plus 2 is also true using the relationships. Now we are required to prove actually that uk plus 2 should be, I do a direct substitution to have a guide of what is expected of me in the inductive step. And I will replace every n in un by k plus 2. That gives 2 into k plus 2 minus 1 all over 2 to the k plus 2. That gives 2k plus 4 minus 1, 2k plus 3 all over 2 to the k plus 2 gives 4 into 2 to the k. So this is what we're expected to prove. If we arrive this expression at the end, it means we have successfully proved that uk plus 2 is true, and therefore un will be true. Now uk plus 2 in the recursive relationship, we can obtain it by replacing every n by k. So it should give us UK plus 1 minus 1/4 UK. And I make replacements of the assumptions I've made in the hypothesis step, which I have that UK plus 1 will be obtained by replacing every n in un by k plus 1. So I get 2 into k plus 1 minus 1 all over 2 to the k plus 1 minus 1/4 UK. Replacing every n by k. In un I get 2k minus 1 all over 2 to the k. Overall we get 2k plus 2 minus 1 gives 2k plus 1 all over 2 to the k plus 1 is the same as 2 dot 2 to the k minus 2k minus 1 all over 4 dot 2 to the k at the denominator. This gives, we have the LCM as 4 dot 2 to the k. 4 dot 2 to the k divided by 2 dot 2 to the k should give 2 into 2k plus 1 minus 4 dot 2 to the k divided by 4 dot 2 to the k gives 1. So multiplying at the numerator we just get that, and that gives 2k times 2 times 2k should give 4k plus 2 minus 2k negative plus 1 all over 4 dot 2 to the k. And this finally gives 4k minus 2k, which is 2k, and then plus 2 plus 1, that is plus 3 all over 4 dot 2 to the k. And actually you can see that UK plus 2 is what we verified to be expecting. UK plus 2, we verified that it must give 2k plus 3 over 2 dot 2 to the k as we have here. So this is true. Hence un equals 2n minus 1 all over 2 to the n for all n belonging to the set of natural numbers. So hope this helped in the difficulties you have been having with series and sequences. I would have to upload more videos, especially involving recursive sequences, because they're actually a trouble with most learners. Finally, there is an app called Briefify. It is on Google Play Store. I have posted the link below the video description. Go and download from Google Play Store, and then you create an account. In that app I post almost every day on basic concepts, summaries, mathematical concepts, and even physics. So you can create your account and follow me there to have more vibes and hints on the various topics and their summaries.